Okay, and welcome to the mock paper for higher level, which is actually May 2014, so actually sitting last year's paper. So here we have our first data analysis question. It's important that you realise that a data analysis question is just that. You don't have to be familiar with the physics behind the question, although it does help if you understand what's going on. Here we have an experiment where Connie and Sophie put an equal amount of water at the same initial temperature into each can. And the cans are all different colours. They vary from the lightest until the darkest. So this must be about absorption rates. So the darker colour would absorb probably the most heat, but we'll look at those results later. Anyway, back to Connie and Sophie. They leave the cans under the lamp at equal distances and then measure the temperature increase of the water. So, if we have a look at the results, okay, Connie suggests that T is proportional to B, where B is the percentage of black in the paint. To test the hypothesis, the graph is plotted as below. Now, while on this page, I'm going to answer question part 1 and part 3, okay? Question A, part 1, asks you to state the absolute uncertainty in T. So if we have a look, we can zoom a little bit closer. You're told to state what the uncertainty is in these error bars. And as you can see, each one increment is equal to 1 degree. Okay, so the error bars are equivalent to 1 degree. Okay. Part 3 asks you to plot a line of best fit. Now, lines of best fit do not have to be lines. You have to look at the points, and if you see a curved relationship, then this is your line of best fit. Okay, now as you can see in this situation here, if you were to plot a line, you would end up missing some points. Now, it could be that they're anomalous, but it's very, very unlikely. So let's have a go at plotting a graph, which is a curve. Okay, and when you're plotting curves, you try and get as close as possible. This is very difficult for me with this app and easier for you. But you try and get as close to as many of the points as possible. And if you can't, if your pattern doesn't quite fit that, you must at least go through the error bars. Okay, so what do we need to take away from this? That lines of best fit can also be curves of best fit. It says state the value of the absolute uncertainty in T. So if we have a look. Okay, so here we can see the question. The absolute uncertainty is 1 degree Celsius. And to comment on, and part 3, we drew the line of best fit already. So if we go back to part 2, comment on the fractional uncertainty for the measurement of T. For B is 10 and B is 90. Now remember, fractional uncertainty is simply uncertainty expressed before you work out the percentage uncertainty, before you multiply times 100, you actually already have the fractional uncertainty. So let's have a look at these 2 points. When B equals 10, T equals 14 degrees. Okay, and when B equals 90, T equals 33. Okay, so our uncertainty is plus or minus 1 degree, so our fractional uncertainty for the first one would be 1 over 14, which gives us a decimal of 0.07. And our second one is 1 over 33, which gives us our fractional uncertainty of 0.03. But the question asks you to comment on the fractional uncertainty. So what you would need to say is that as the reading for B gets greater and the temperature gets greater, the fractional uncertainty gets smaller. I know it's common sense, but it's what it's asking you to say. Okay, part 4, outline why the data does not support the hypothesis that T is proportional to B. This is basically asking you to explain what proportionality looks like. Now, the data does not support it because it's not a straight line graph, okay, line graph, and it does not go through the origin. Now, this is a very common question. The origin. And that's 2 marks. The question continues with a further hypothesis. Sophie this time suggests that T equals K, B to the power of a half plus C, where K and C are constants. To test whether or not the data supports this relationship, a graph of T against B to the power of a half is plotted as shown below. The uncertainty in T is shown and the uncertainty in B to the half is negligible, as before. So, use the graph to determine the value of C with its uncertainty. Okay, now there are a couple of steps to this. First, let's work out the value of C. We are dealing with a straight line graph, y equals mx plus c. And if we look at the equation, y equals k b to the half plus c. Again, it's really obvious. I don't know why I wrote it down again. But what we're looking for is the intercept. So when x equals 0, what is our intercept there? And if you look very, very closely, okay, you can just about make out it's about 4.6. Okay, which is there, that point there, 4.6. Okay, but the mark scheme will accept anything from 4.5 all the way to 4.9. It's very generous of them. Okay, the actual answer is 4.7, although it looks like 4.6 to me. Oops. Let's have a look now at the error. Okay, now in order to find the error of a intercept, you actually have to work out, and this is going to be really tricky for me to do with this, so hopefully you'll be able to do this with a ruler. You actually have to do your maximum and minimum gradients and then look at the maximum. So when you do your maximum gradient like this, okay, and then you do your minimum gradient, and your maximum and minimum intercepts will give you the uncertainty for the intercept. Okay, so I'm going to try and do that with a straight line function. Actually, that was harder than I thought. So I tried to do it freehand. You guys have to use a ruler. So let's have a look. Here you can now see we have a plus and a minus. Okay, oops. Let's see if I can now make that a lot bigger. Okay, so I've got a plus or minus of 1 and 1.5 degrees. So I'm going to use the maximum, which is plus or minus 1.5 degrees. This is a very straightforward question. The unit of K, well, it's temperature in degrees, and there are no units on this side, on this axis, so the gradient would have units of degrees. Okay, this is a question about simple harmonic motion. We have a spring attached to an object which is oscillating about point O. Outline the conditions necessary for the object to execute simple harmonic motion. The defining relationship for simple harmonic motion is that acceleration is proportional to displacement. Okay. From the origin. But in the opposite direction. But in the opposite direction. Okay, now there are variations on this. You can say force is proportional, the restoring force is proportional and opposite in direction to the displacement. But either of these two will do. Okay, so here we have a displacement time graph for 3 time periods. So displacement time. Part A, label where with the letter A, a point where the magnitude of the acceleration of the object is a maximum. As you've already mentioned, acceleration is proportional to minus displacement, so they're proportional. Wherever the displacement is a max, then the acceleration will be a maximum. So A would go here, or here, or here, or here, or here, etc. Part 2, label with a letter V the point at which the speed of an object is a maximum. A displacement time graph will give you velocity by looking at the gradient. So if you have a look at the gradients here at the top, the gradient is flat. This gives us a value of V, which is 0. And that gradient starts to increase, the slope gets steeper, until a maximum, which is here through the origin. Okay, so the speed would be here, V, a maximum, or here, or here, or here, etc. And then part 3 is sketch on the same axes how the displacement varies with time if a small frictional force acts on the object. Well, the frictional force will affect the amplitude. So we will begin in the same place, but our wavelength will be completely unaffected. So you must make sure that you respect the period. So this goes down, but then slowly starts to reduce its amplitude. Okay, now it's small force, so it doesn't go down to 0, and that will do. Okay, so you can see that the amplitude is reduced, but the wavelengths and the period, not the wavelength, is respected. It stays the same. Right, so this is a question about resonance. We see a variation of frequency with amplitude, driving frequency with amplitude, and we're asked, with reference to resonant and resonance frequency, comment on the shape of the graph. So you must mention these 2 concepts in your answer. So let's have a look. We can see that as the driving frequency increases, let's start with increases and approaches the resonant frequency, okay, the amplitude increases up to a maximum at resonance. And you can, if you want, reference the graph, so you can put an X there and say at X, etc. On the same axes, draw a graph to show the variation of F with F of amplitude when the frictional force acting on the object is increased. So this is just something you need to learn off by heart. One of the major differences when you have damping, when you have friction acting, is that the peak is very much reduced, and it's also slightly to the left here. So you have a reduced amplitude in everything, and then you have a slight peak, but it's got nothing. It's nothing like the one above. And you have to make sure that your amplitude is less everywhere. Oops, which I haven't done there. Okay. So 2 marks, one for a reduction in amplitude, and a shifting slightly in that direction of the maximum peak. Alright, here we go. We have sound being emitted by an object towards a stationary observer. If you remember, there was 2 situations. one where the source is moving and one where the source is standing still. Okay, so this is the first situation. And what we have is a Doppler effect, which looks like this. The waves on one side getting squashed, and so therefore closer together. Okay, that should be further apart like that. Okay, so this is our moving object, and this is the speed of our wave, c. Now explain using a diagram, and that means you do have to use a diagram, why the new frequency, this f dash, is greater than this f. And that's because basically the speed of c, the speed of the sound, stays the same. Okay? And if you remember the relationship for speed equals frequency times wavelength, wavelength, due to this Doppler effect, is reduced. Okay, so what we have here is if c stays the same and the wavelength goes down, frequency must increase. And that's your 3 marks. Now the frequency f is 275 hertz. The source is moving at a speed of 20 meters per second. The speed of the sound in air is 330. Calculate the observed frequency. What you have in total 4 relationships, and you just have to remember that when the object is moving towards a stationary observer, that you use this relationship. V minus U equals F dash. Okay, and now you just have to substitute the values in, which are 275, which is the frequency. You have, the speed of the sound, 330, okay, and 30, minus the speed of the observer, which is 20. And you should get a value of 293 hertz. Okay, so part B, we now have a diffraction question. We have a single space, single gap, but this is sound wave diffraction. So the sound detector moves along x, y, and what we need to plot first are a diffraction intensity pattern as the detector moves from x to y. So if you remember, there's a very specific pattern, which means a decrease in intensity down to 0, and then the next one's really small. The mark scheme says less than 1/3 of the original peak, so make it really small, and then don't forget to be symmetrical that way. State the effect on the intensity pattern of increasing the wavelength of sound. Okay, so I'm going to squeeze in a little picture and give you a bit of a full explanation on this. If you remember, we had a relationship for single slit diffraction, which was the angle, which I'll talk about in a second, was equal to lambda over W, W being the gap size. Okay, and this was the wavelength of the light. And if we positioned our frame of reference from the middle of the gap, okay, when we derived this formula, we talked about 2 wavefronts meeting where there was a zone of destructive interference. Here, destructive. Okay, and this distance we're going to call x, and we're going to call this distance y, okay? And the angle that we've mentioned in the formula, this angle, is this angle here, okay? Now, almost finished. We're going to talk about this angle again. That angle is equal to tan of the angle. But because we're talking about very small magnitudes or very tiny, tiny sizes, we can forget about the tan and we can just leave it as the angle. And that angle is equal to this side divided by this side, equals x over y. Okay, so if we go back to the original formula, we have x over y equals the angle, which also equals the wavelength over the gap size. So back to the question. State and identify the intensity pattern of the difference in the intensity pattern of increasing the wavelength. Well, if we increase the wavelength, okay, this will be bigger. So therefore, let's have a look at the size. The angle would be bigger. And why is the angle going to be bigger? Because x is bigger. So what's going to change? This distance and nothing else. Okay, because W stays the same, the intensity of the light. So the only change is the position of the zero intensity, which will be further away. And the best thing to do in an exam is to actually show this. Okay? Okay, next question about polarization. What is our definition of polarizations? Well, polarized oscillations are in one plane only. Okay, and unpolarized are the oscillations are in all directions. Okay, and state-wise sound waves cannot be polarized because sound waves are, the vibrations are in one plane only. Sound waves are longitudinal or vibrate along the same line as the direction of motion. Okay, so basically anything that you say to state that there's only one plane of direction. Okay, so now question 6 from section B. We have a question on solar radiation and greenhouse effect. So using this data, we're first asked what the Stefan-Boltzmann law for a black body is. If you look on the data sheet, you're actually given the relationship. It's just not labeled, so you have to just familiarize yourself with each of them. So power, if we look at the relationship, power equals sigma, which is the Stefan-Boltzmann constant, area, T4. So if that's a relationship, what is the law? Well, the law is that power is proportional to area and also proportional to absolute temperature in Kelvin to the power of 4. Part B, we're still on the same relationship. Deduce that the solar power incident per unit area at a distance d from the sun is given by the following. So using this Stefan-Boltzmann relationship, power is sigma area over T4. Okay, this is basically the power of the emitting object, and the emitting object is the sun. So by area, we actually mean the surface area of the sun. So what is the power that's being given off by the sun? Well, it's sigma times the surface area, which is 4 pi r squared. Okay, remember that 4 pi r squared is how we work out the area of a sphere. Okay, so we're always imagining the sun as a giant sphere, and every single part of it, all of its surface area, is emitting heat. Okay, and then times t to the power of 4. So this is our emitting object. Okay, but that's only half of it, because the question is about the solar power incident per unit area at a distance d. In order to do this, we need to consider, okay, I'm going to draw this a little bit lower down here, that the sun is a hot object that's emitting heat. And then you have the Earth at distance d. Okay. And we have to consider how much of the sun's power still reaches the Earth at this new distance. Because remember that intensity, power per square meter, does depend on the distance from the source. Well, we imagine a giant sphere. Okay, well, not a very well drawn one, but we have this giant sphere. So all of the sun's intensity is being distributed along the surface area of this giant sphere. So if we work out how much of the sun's energy is falling per square meter at this distance d, we can work out the power per square meter. Now, how do we do that? Well, we need the surface area of this sphere, which is 4 pi d squared. This giant sphere has this surface area. And so we have the power of the sun, and now we divide it by the surface area of that giant sphere. And we can see that on the Earth at distance d, we get, let's cancel out 4 and let's cancel out pi. We get P equals sigma r squared T4 over d squared, which is what was asked in the question. So now you have this formula, you just have to put some values in. Okay, so I'm going to write them in here, but pretty much they're given on the results table or on the data sheet. You have to use the constants on the data sheet. So the Stefan Boltzmann's constant, 5.67. In fact, I'm going to write these all in. Okay, so what does that equal? You should get an answer of 1.4 times 10 to the 3. And don't forget units, watts per meter squared. Okay, so part D, state 2 reasons why the solar power incident per unit area at a point on the surface is likely to be different from your answer in C. Well, basically, because there's a lot more going on. Okay, so if we think about it, 255 Kelvin, that's below zero. That's actually really cold. Luckily, and it is strange to say this, but luckily we do have greenhouse gases. Greenhouse gases, okay, absorb and re-emit, increasing the temperature of the Earth. The Earth's temperature. Okay. Outline why the burning of fossil fuels may lead to an increase in the average surface temperature of the Earth. Well, this is an easy question, if you burn fossil fuels, you increase the amount of CO2 and other greenhouse gases. So you increase absorption and re-emission of heat. And this is a very common question. Okay, this is a question about orbital motion. A spaceship moving around a planet. What is the name of the force that's causing this centripetal force inwards? This is a gravitational force. Gravitational force. Okay, it's one easy mark. Part 2, explain why astronauts inside the spaceship should feel weightless, even though there is a force acting on them. Well, the reason why we feel weightless is because the floor doesn't exert a force on us. If you think about the spaceship, if you're in that spaceship, make it a bit bigger, if you're bandying around inside that spaceship, you are also moving in this direction, and you also have a force acting on you, but so does the spaceship, and your acceleration is the same as the spaceship's acceleration. So you don't actually experience a force, like you don't feel the spaceship exerting a force on you. So let's say if your feet were there, okay, the ship wouldn't be hitting your feet. you would both be accelerating in a circular path. So you don't actually feel this reaction force, which you interpret as gravity. So to put that into words, and it is a tricky question, let's have a look. The astronaut and the spaceship both accelerate because they both experience a force, and there is no reaction force between the surface of the spaceship and the astronaut. Okay, now we're going to deduce the speed as it moves around in a circle as gm over r. And let's have a look. So we are accelerating. That acceleration is equal to g. Okay, so what is g? G is the gravitational field strength. And we have a relationship for that. If acceleration equals g, and g equals gm over r squared, okay, we have an expression for acceleration. But we also know through circular motion that acceleration is also equal to v squared over r. Okay, so if we put these two together, we end up with v squared over r equals gm over r squared. And in order to make v the subject of the equation, I can cancel out one of the r's, and I can square root g. So I end up with v equals square root of gm over r. Okay, so now we're going to talk about energy. We have expressions for kinetic energy, gravitational potential, and total. So, first situation, a spaceship passes through a cloud of gas, and we have a small frictional force. State and explain the effect of this force on the total energy of the spaceship. Well, just like any other situation, friction means that there is thermal energy transfer. Transferred. So there is a decrease in the energy, or the total kinetic and potential. So what does this then have, what is the consequence of this on the speed of the spaceship? Okay, so this is a bit of a tricky question. As the satellite loses energy, it actually loses the energy in the form of gravitational energy. So the satellite actually moves a little bit closer to the Earth. Okay, so this is just something you're going to have to remember. It's very rare that this gets asked, but any orbiting satellite, if it loses energy, that means transfers it into thermal energy, it will fly a lower orbit because it's converting that gravitational potential energy. It does, however, increase its velocity, which is a bit strange, but let's have a look at a formula for our speed, which equals the square root of gm over r. If we reduce r, if we make this smaller, it actually makes our value of v greater. And so therefore the answer is v increases. Right, question 7, which some of you attempted. Define the term unified atomic mass. The term unified atomic mass is 1/12 of the mass of a carbon-12 atom. Okay, that's a very simple definition. We now have the mass of Einsteintanium 255, and you have to convert that into mega evolts per coulomb squared. But for this, we need the data booklet. Okay, because in the data booklet, I just have a quick look at it, we are actually given the value of the unified atomic mass unit in megaevolts per coulomb squared. So 931.5 is 1 U. So we multiply that by the number of U's, 255.09. Okay, and that will give us our answer, which is 2.38 times 10 to the 5 megaevolts per coulomb squared. Describe the phenomena of artificial transmutation. Okay, so this is something that's come up a few times in this paper, and the multiple choice as well. Basically, it's when a particle is fired or at a nucleus and a new substance forms. Basically, it's a form of it's making an artificially radioactive substance. Part C, when particle X collides with a stationary nucleus, a new substance, potassium, and 1 proton is released. And the first question we're asked is to identify that X element. Okay, so if we have a look at the numbers, let's have a closer look. We have a total here of 41, so therefore this must be a 1. Okay, and we have a total here of 20, so we must have 0. Okay, because that's 20. So the only thing that will give us this kind of atomic arrangement is a neutron. Okay, so the answer to this one would be neutron. And now part 2, why will the reaction only occur if the initial kinetic energy is greater? Well, the initial rest mass of the products is greater than the reactants. And in order for this to take place, there has to be some extra energy, and this is from the kinetic energy of the reactants. Before the reaction occurs, particle X has this much kinetic energy. Determine the total combined kinetic energy of the potassium nucleus and the proton. So let's think about the energy that has. We have energy before, which is due to this kinetic energy. Yeah, and then after that, if we remember, E equals mc squared. These kinds of reactions release energy, a mass, because of the mass defect. Okay, so we're going to call this, I'm going to call this Einstein's energy, just to relate it to this equation. So when the reaction takes place, you have this little Einstein energy, which is due to the mass defect, plus, according to this, the kinetic energy of the potassium and the proton. So how are we going to work this out? Well, if we can work out the mass defect and its equivalent value in megaevolts, okay, we have the kinetic energy before, we just need to work out basically this minus this. Okay, so how do we work that out? Well, if we use the data given at the beginning, we should be able to work out the mass defect in megaevolts, and I'm going to do that now. Okay, so the relationship was calcium plus X, the neutron, equals potassium plus the proton. So if I subtract this side from this side, I should work out the mass defect. Okay, so here it is written out. We have the mass before, but in megaevolts, minus the mass of the products, and we end up with a mass defect, but in megaevolts. So therefore we have the energy released as 0.573. Okay, Now, if we subtract this from the kinetic energy of the proton at the beginning, we should have the leftover kinetic energy. Okay, so we're going to do that now. Okay, so you can see it here now. The kinetic energy minus the mass defect gives us the kinetic energy of the fragments after the reaction. Back to something a little bit more straightforward. Define the term radioactive half-life, and it's a time. So it's the time for half the activity or the number of radioactive nuclei to decrease by a half. Okay, part 2. A sample of potassium has an initial activity of 24 times 10 to the 12. On the axes, draw the variation with time of the activity. So you have to show that you understand this premise of half-life by coming up with the coordinates. In one half-life, which is 8 minutes, okay, you should have half of the original activity, which leaves us with 12 times 10 to the 12. Okay, in 16 minutes, you should have half of that, and 10 to the 12, and then so forth until you plot all the given points. So I'm going to do that now. Okay, so you can see my half-life graph with 3 coordinates worked out. Okay, so if we go back to the questions, determine the activity of the sample after 2 hours. Okay, now 2 hours times 60 minutes, 120, and if you divide that by 8, it coincides as 15 half-lives. So if you can either work this out really slow, like do it at your own pace, but if you work out 15 half-lives, you can just keep reducing. That's 1 half-life, 2 half-lives, 3 half-lives, and eventually you'll get to the right answer. Or you could just divide the activity 24 times 10 to the power of 12 divided by 2 to the power of 15. Okay, and that should give you the right answer, which is 7.3 times 10 to the 8. BQs. Don't forget the units. Okay, part B is about heat engines. Here we have the pressure volume graph for a process, a piston of an engine. What is meant by an isothermal process? Well, an isothermal, you should remember, is a process where the temperature is constant. Okay. Show that process AB is isothermal. So I'm going to make some space here and we'll sketch the graph. In this we have P and we have V, and those two positions, A and B, should show, using the ideal gas equation, we know that PV over T for any gas is constant. So by changing the volume and the pressure, you would get a new situation, P2 V2 over T. Okay, so this would be at A and this would be at B. Now, in order for them to be constant and for temperature to be equal, in order for this temperature to be equal to this temperature, then the product of pressure times volume should be equal. Okay, and if that's the case, then it's true that the temperature is the same. Okay, so if you look at the values of P and V for both A and B, we have 8 times 10 to the 5 and times 2 times 10 to the minus 3, that's position A. And if we have a look at position B, we have 4 times 10 to the 5 times 4 times 10 to the minus 3, which is position B, and that would both give you 16 times 10 to the 2. So therefore, pressure and volume before equals pressure and volume after, and the temperature must be constant. State the nature of process BC. Well, if we draw the rest of this graph, it looks like this. Okay. And the rest of the process BC has constant volume, so the volume does not change. So what you have is an isochronic process. Okay. During the cycle A, B, C, and D, the net work done by the gas is 550 joules. This is actually a really straightforward question, and though it's tempting to start working out areas, bear in mind it's only 2 marks. Now, if you start at A, go down to B, C, D, and then back to A, there is no change in temperature. So therefore you have no internal energy change. Okay, so therefore delta U equals 0. Okay, so that means that Q equals W and must equal 550 joules. Now a very common question, why is it not possible for this energy to be 100% efficient? Because energy is always lost to the surroundings. So therefore, not all energy absorbed by the gas and it is not all converted to work. Okay, which is a very common question about this kind of process.